Okay, so the first time we saw that, well, of course, there's quite a bit that we didn't do about the context and the possible different proofs of the Perron Frobenius theorem. But we could see that, in a pretty short period, you could get get through a proof and some pretty good idea of what was going on with the basic Perron theorem, along with your diligent study of these notes after the first lecture. So the Perron Frobenius theory can be generalized in a few directions. The most important has to do with functional analysis, where there are operators on Banach spaces, and theorems which mimic the Perron theorem. So this is a kind of multifaceted, complicated thing. You'll probably see something of this with Mark Pollicott's talks next week. He's one of the masters of the subject. So I'm not going to try to explore the generalizations in that direction. Another direction is to consider complex matrices rather than real matrices. I'm not sure that there's a really general theory there, although there are results. But this is another direction that I'm not going to try to pursue today. And these can be also pursued in tandem. You can look at operators on complex Banach spaces and find theorems. Okay, so what I'm aiming to do today is to consider a Perron Frobenius theory for infinite matrices. So these are, well, natural numbers by natural numbers indexed, non-negative matrices. And there's a theory due to Verre-Jones, essentially, which is at least we can have some hope of stating and coming to some understanding of in a lecture. And it's really a great theory. It's quite basic, and so I think it's well worth your time for the next hour or so. Okay, so here we go. So this Perron Frobenius theorem, again, it comes from Verre-Jones, especially his 1967 paper, quite a while back. So in this lecture, A is, again, capital natural numbers by natural numbers, or perhaps a finite matrix with non-negative real numbers. And as in the finite case, this kind of analysis for the Perron Frobenius theory goes by cases. Well, case 1, A is irreducible with period 1. Those statements mean the same thing as in the finite case. For every entry of the matrix, there's some power of the matrix, which makes it positive. That's what irreducibility is. Period 1 is that the greatest common divisor of the traces which are of the powers which have positive trace is equal to 1. Okay, and then in the finite case, this corresponds to primitive, this class 1. And the second class is irreducible, where there can be a period which could be any natural number. We saw in the finite case that we could reduce our understanding of that to the first case, which is the central case from my viewpoint. And then there's some kind of a statement about general non-negative matrices. So the reductions aren't so different from the reductions in the finite case. So we'll focus on the first case. Okay. Now, when A is finite, again, this class 1 is equivalent to saying that the matrix is primitive. It's non-negative and it has a positive power. Every entry is positive for that power. For an infinite matrix, it's too restrictive to say that some particular power of the matrix has every entry positive. That's too restrictive, and it's not necessary. So the description here is irreducible with period 1. Okay, so let's. Now, in the finite case, the Perron theorem is a very uniform statement. It holds for every irreducible period 1 matrix. Irreducible period 1 is also called irreducible aperiodic. I'm not totally fond of that because there are a lot of periods that are in there. But anyway, it's English instead of a name, so I'll stick with it. So all aperiodic irreducible finite matrices, have this same homogeneous behavior for the Perron theorem. Now, in the infinite case, that's not true anymore. The aperiodic irreducible matrices we can split into 4 classes, and this split will reflect how the conclusions and the corollaries of the Perron theorem for finite matrices break down. Okay, so there's a kind of a gradation of how things go in this infinite case. And again, in this lecture, I hope that we can come to some understanding of some statements and some key ideas for this infinite case. It would take another lecture or two to go through a proof, and the proof is intricate enough that it should be done in private anyway. Okay, so let's remember what the Perron theorem was for finite matrices. I never write it down with the same words twice, but the content for my choice is equivalent. So here we go, the Perron theorem. If A is an n by n primitive matrix, there's some positive real number lambda such that A has a non-negative eigenvector with eigenvalue lambda. And this non-negative eigenvector must be positive because a power of A is positive and has that same eigenvector. Also, this lambda is a simple root of the characteristic polynomial, and it's strictly greater than the modulus of every other root of the characteristic polynomial. Okay, so that's our Perron theorem. Now the critical step, the first step, was to get that non-negative eigenvector. That was easy for us, right? We just used the Brouwer fixed point theorem. There are other ways to get it, but this is not so hard for a finite matrix. Now, for that step, we use the action of the matrix as an operator on Rn. Matrices are multiplying elements of this finite dimensional Banach space. Well, if you think about infinite countable, natural numbers by natural numbers, irreducible aperiodic matrices, we don't have a good space on which they operate. If you think for a while, you realize this is really a problem. So we don't begin with any kind of nice space, and so we don't have an analogous argument. This problem already also arises when you consider the functional analysis generalizations. But you have operators on Banach spaces. There are generalizations of these finite dimensional fixed point theorems. You have something to work with. Here we don't in this generality. So Vere-Jones solved this by giving a very different kind of argument, which involved formal power series defined somehow locally in terms of the matrix. So we'll do this. So it's going to take us a while to develop all of this stuff, but here we go. Well, first of all, let's do something that's quite easy to warm up. We can think of a matrix as a labeled graph. Okay, and remember, a graph for me is always a directed graph. And this is for a couple reasons. One, the language, and also for visual support. If you're not blind, good chance the best part of your brain for mathematics is the visual part. So the more you can engage that, the better. So given this matrix A, we associate to it a labeled graph, labeled directed graph. In the following way, I think it will be obvious what I mean as if I just write an example. So here's the matrix. A is 3 pi 0.430. Well, there's row 1. 1 is now a vertex. There's row 2. That's a vertex. The 1, 1 entry, being non-zero, inspires me to draw an edge from 1 to 1. And seeing that number 3 lets me label that edge by 3. Okay, well, from 1 to 2, there's another edge labeled pi. From 2 to 1, there's an edge labeled 0.43. What about the edge that's labeled 0? Well, I could write it. The computations wouldn't change, but it's convenient and concise not to bother writing those edges which are labeled 0. Okay, so I don't. So there we go. There's a directed graph. And clearly, if I have such a graph, I can go back to the matrix as soon as I assign integer indices to the vertices. So we can go back and forth between these two pictures, these two formulations. Okay, now a little terminology. A path P of length n in this labeled graph. So this is GA coming from A. So a path of length n from I to j is just a finite sequence of n head-to-tail edges from I to j. So here I've taken an edge to be given by a pair, which is first the initial and then the terminal vertex of the edge. So for example, the path 1 to 2, 2 to 1 would look like that. Okay, so there's a path of length 2, those two edges. There's an initial vertex and there's a terminal vertex. Okay, so we have a path from the initial vertex to the terminal vertex corresponding to some legal transitions in the graph. This path is a loop if the initial and terminal vertex are equal. Okay, and it's a first return loop if along that path I never return to the initial vertex before the terminal vertex. Okay, and well, I say an n path is a path of length n. An n loop is a loop of length n. The length is the number of edges in the path. Okay, and we restrict from here to matrices such that we have well-defined powers. If we have infinite matrices, which are non-negative, think of an infinite matrix in which every entry is 1. Well, if we square it, every entry is infinity. We'll only consider matrices for which, when we take a power, every entry is a well-defined non-negative real number. Okay, now if we have a path has a weight. The weight is simply the product of the labels along the path. So for example, for this path, 1, 2, 2, 1, the first label is pi. The second label is 0.43. And so, the weight of this particular path is just 0.43 times pi. All right. Now, so the weight of an edge is just, from I to j, is just the ij entry of the matrix. And if we take a to the nij, a to the nij is going to be the sum of the weights of the length n paths from I to j. Okay, so this is kind of a key thing, the relation between matrix multiplication and paths in the graph. Okay, now there are two series which are totally fundamental to this Verre-Jones theory. I'm calling them F and T. And how do we get these series? Well, we pick what I'm calling a base index in the natural numbers. It doesn't matter what index we pick. Everything will turn out the same independent of the particular choice. And then once we pick this base index, we define two formal power series, F and T, which are critical for this theory. Okay, so our base index is 1. And here's the definition. The pieces of the definition. T sub n is a to the n 1, 1. The 1, 1 entry of the nth power of the matrix. This is the sum of the weights of the n loops from 1 to 1. Okay. Now Fn is the sum of the weights of the first return n loops from 1 to 1. Okay. So the difference is just first return versus all returns. Okay. And Well, f of z then is going to be this sum, and t of z is going to be f and t are the formal power series which have those coefficients for the powers of the variable. Okay, and well, of course, this f depends on the matrix A, but when this is understood, I'll just suppress that. Now, what's easy to check is the following. If we take Tm plus n, that's greater than or equal to the product, Tm times Tn. Basically, if we take the product, we're considering weights of paths which are concatenations of m loops and n loops. Okay, so we have that, but then there might be some others that arise as we look at longer paths. So that's why we have this superadditivity. And once we have the superadditivity, well, we can consider the supremum of the nth root of Tn, and that will be a limit. It's not difficult to check that this will be a limit, and we say that lambda is this limit. And this limit does not depend on the choice of the base index. So we define the Perron value, lambda a of this a, to be this number lambda. Okay. Now this lambda might be infinity. Okay, but okay. Now the radius of convergence of this series T, of course, the radius of convergence of a series is going to be the reciprocal of the growth rate, the lim sup over n, of the nth root of the coefficients by Hadamard. And this radius of convergence, by definition of lambda, is 1 over lambda. Okay, so we have a formal power series, but it also has a radius of convergence as a function from the complex plane to the complex plane. Okay, well, here, just to be safe, here are some examples. Suppose we have positive numbers a, b, c, d. And we're looking at the base index 1. There's only one first return loop of length 1. Okay, and it's labeled A, so the first coefficient, F1, is just A. What are the first return paths of length 2? Well, the only thing that can happen is that you can go from 1 to 2 and from 2 back to 1. And in that case, you see that the weight is BC. What about length 3? Well, you can go from 1 to 2, 2 to 2, 2 back to 1. Length 4, 1 to 2, stay at 2 for 2 units of time, back to 1. So in this example, it's pretty easy to compute what f of z is. It's a times z plus bc times the sum from 0 to infinity d times z to the k plus 2. You can compute it. What about t of z? Well, the first one's pretty easy. T1 is equal to F1. That's A. What about the second one? Well, we have the weight of the first return path, but now there's also a path which is not a first return path, which is the path obtained by going from 1 to 1 to 1. What's the weight? The weight is a squared. Okay, so that's it for for loops of length 2. And so we have this coefficient for T2. Okay, and now I say, and so on. It's not as immediately obvious what so on is for this example. Now, what's easy to check is that if A is finite, then lambda A is just the usual spectral radius by the spectral radius theorem. Right? The spectral radius is the growth rate of the entries of the matrix. And also, this lambda A we've defined is the supremum of the lambda B such that B is a finite principal submatrix of A. Okay, well, that's a good sign. right? You know, the Perron value for this infinite matrix, you know, we'd be very uncomfortable if it were not the limit of a suitable increasing sequence of principal submatrices Perron values. So it is. That's what it should be. Whoa. Okay. Now there's an essential functional relation, which is the following. 1 over 1 minus f is 1 plus t. It's a relation of power series. And but let me, before I say anything more about that, let me just say something about what 1 over 1 minus f of z is. So this is an equation of formal power series, and by definition, 1 over 1 minus f is 1 plus f squared plus f cubed, etc. Okay? Now, we have infinitely many series we're adding up, so there are infinitely many coefficients of terms, but f has no constant term. So when we take a power f to the k, that only involves terms of degree k or greater. So if I want to find, for example, the coefficient in this series of z squared, I only have to look at f and f squared. Okay, so this is a well-defined formal power series. Now, if I have a real number which is bigger than the radius of convergence of this power series, well, it makes sense to say that when we evaluate at that number, we get 1 over 1 minus f is infinity. Okay? Okay, and from the series, you can also see that the radius of convergence of f is less than or equal to the radius of convergence of t. Okay, and this relationship is going to be quite important. Okay, now here's an example. Suppose we have a single vertex with a self-loop labeled 2. In this case, f of z is 2z. Well, we can write what t of z, 1 plus t of z is and check this functional relation. For the proof of this relation, it comes down to just establishing a recursion formula for the coefficients. This is not difficult. I'm going to skip it just because we have only so much time. Okay, now so now we're prepared to make some definitions to divide these irreducible period 1 infinite matrices into classes, the classes that will correspond to conclusions in the Perron Frobenius theory. Okay, so I'll let T of 1 over lambda denote the sum Tn 1 over lambda to the n. In other words, I take this series T and I see what happens when I put in 1 over lambda. Okay? It might converge to some positive number, or it might diverge to plus infinity. Okay, and now definition, A is transient, abbreviated capital T, if T of lambda is finite, and it's recurrent if T of lambda is infinite. Okay, so that's the first fundamental distinction. And for the Perron Frobenius theory, the transient matrices are the bad ones. And almost everything goes wrong. Okay, so it's not like the finite case. There are matrices which are just very ill-behaved. Okay. All right. Now, the recurrent matrices we can divide into 3 classes, and for this we also involve the formal power series, which is the derivative power series. And now comes some more definitions. A is null recurrent, NR, if it's recurrent and this derivative series at 1 over lambda is infinite. Okay, so if I take f prime of z, put in 1 over lambda, the series diverges to infinity. And by definition, the matrix A is positive recurrent if it's recurrent and f prime at 1 over lambda is finite. Okay. So this great Verjones work of 67 gave the theory for these 3 classes, which I'm calling T, NR, PR. He used another notation. We'll do notation later. But let's also single out another class, which is quite important. And this is a class which, well, it might have different names. For today, I'm going to introduce a name. I'm going to call this class exponentially recurrent. Okay, and A is exponentially recurrent if the radius of convergence of f is strictly less than the radius of convergence of t. Okay, so t was again the sum of the powers of f, and it can happen that f has a smaller radius of convergence than t, as it will whenever we have a finite matrix. Okay, so an example perhaps I should mention, just to try to encourage the idea that finite is good. Suppose we looked at the matrix which is just the matrix 2. Okay, and well, here f of z is 2z. Okay, I think I know what the growth rate of these coefficients are, fn, as n goes to infinity. Fn is 0 except for f1. So here the radius of convergence is infinite. Okay, but if we take the series t, you know, t of z is 1 over 1 minus 2z. The radius of convergence there is 1/2. Okay, so this is the simplest example, but we have this behavior always for the finite matrices A. Okay. Now it'll turn out that recurrent, the class of all recurrent matrices, contains the class of positive recurrent matrices. Well, that's pretty clear. But also it contains the exponentially recurrent ones. Okay. And the Perron Frobenius properties will improve as we move down this list. And the exponentially recurrent ones are the class that is very close to finite primitive matrices for the Perron Frobenius theory. Okay, so that's the good class. It's the exponentially recurrent. Okay. All right, so let's start looking at these classes. So here are a list of some properties which, as conclusions or corollaries of the Perron theorem, hold for every finite primitive matrix and also hold for every recurrent matrix. Okay, so this is something good about Perron Frobenius, which survives to the class of recurrent matrices. Okay, well, the big deal, we have the non-negative eigenvectors. Okay, and these are non-negative eigenvectors for the Perron value lambda. These vectors being eigenvectors for the irreducible period 1 matrix must be positive vectors. Okay, so that's the very first step, and that's there. The non-negative eigenvectors for number 2, the non-negative eigenvectors for lambda are unique up to scalar multiples. And here's an important one. If u is a non-negative vector, of course here a vector is an infinite vector, and ua is less than or equal to lambda u, that implies that ua is actually equal to lambda u. That's a feature of the finite, one of the features of the finite case. All right. Now, what about transient matrices? Well, none of those properties are guaranteed for transient matrices. A transient matrix might have no non-negative. Oh, by the way, it will be the case often that I make a statement about a right eigenvector or a left eigenvector, and it'll be pretty obvious that I could have done it the other way. So anyway, and that's the case here. So a transient matrix might have no non-negative right eigenvector for lambda at all. It might have linearly independent right eigenvectors. That's kind of nasty. It could have a positive vector, which is an eigenvector for an eigenvalue which is bigger than the Perron value. Okay. that sounds pretty weird, but you know, we'll see an example where you can kind of see how that happens. Okay. So you know, these things can't happen in the recurrent case. Well, what is there something systematic about the transient matrices? There will always be a positive vector, which is a kind of sub-eigenvector for the Perron value, a vector v such that AV is less than or equal to lambda v, but AV is not equal to lambda v. Okay. Something that can't happen for recurrent. Okay, now here's this transient example, which I'm hoping might be helpful. So suppose we have some numbers, epsilon 2. That's epsilon subscript 3, not epsilon times 3, and so on. And let's look at a matrix which has the following shape. It's 1, 2 entry. Okay, row 1 looks like this. Row 2, okay, now we do a little perturbation of 1 here. Make this stochastic. Row 3 is like so, and so on. Now, if these epsilons are all 0, then we have a matrix. Well, it's not nilpotent because no power is 0, but every entry under all large powers becomes 0. Okay, and so that's you can kind of easily believe that you could not without difficulty check that if you choose these epsilons positive, but decreasing sufficiently fast to 0, you can get a matrix which has a Perron value which is positive but as small as you like. Okay? That follows from the finite approximations, right? Because if you want to control the finite approximation spectral radius, well, you can certainly make that very small by choosing these epsilon small successively down the way. And because the sup of the spectral radii of the finite matrix approximations is the Perron value, that controls the Perron value for A. Okay? Well, but this is a stochastic matrix, right? So the column vector, which has got every entry 1, is going to be a right eigenvector with eigenvalue 1, which is bigger than the Perron value. And if you do this, it's not hard to check that you can solve for a left eigenvector, which is also positive eigenvalue 1. Okay, so this is a real unpleasant example, but also a very simple one which shows how things can go wrong. Okay, and this matrix has to be transient. Okay, now what about positive recurrent matrices? Well, now I can talk about convergence of matrix powers. And when I'm looking at these infinite matrices, convergence means convergence entry-wise. If you look at some entry, then there's convergence in that entry. Okay, now suppose that L and R are positive left and right eigenvectors for A. And by abusive notation, let's let L dot R denote the sum L sub n, R sub n. Okay, just it's abusive notation because L is a row vector and R is a column vector. Now, if A is positive recurrent, then L dot R is finite. Then we can normalize. Multiply by one of the eigenvectors by a suitable positive number, and we can require that L dot R equals 1. And then in that case, just as in the case for finite A, adding another parentheses to make a well-formed formula, if we take the nth power of 1 over lambda A, it converges to this matrix, which is R times L. And R is a column vector, L is a row vector. If we take the product like this, we have a matrix of the size of A. Okay, on the other hand, if A is null recurrent or transient, the limit's 0. Okay, so that's a step up for positive recurrent. Okay, and now what about exponentially recurrent? All right, well, this is the class which enjoys essentially all good properties, Perron Frobenius. So in addition to the positive recurrent properties, we have the following. If we look at this convergence of 1 over lambda a to the n converging to RL, this convergence is exponentially fast. Okay. Now, it's not uniform convergence. Okay, that's too much. But if you look at any entry and you look at the convergence in that entry, that convergence is exponential. Which means, of course, that for each entry there are constants c greater than 0, 0 less than kappa less than 1, such that for all n, if we take the difference between 1 over lambda a to the n in that entry minus RL in that entry, that's smaller in absolute value than c times kappa to the n. Okay. Another good thing. If we have A exponentially recurrent, and we have B a matrix such that 0 is less than or equal to B less than or equal to A, and B is not equal to A, then the Perron value for B is smaller, strictly, than the Perron value for A. Okay? And for a finite matrix A with a non-zero spectrum, okay, now I'm going to say something about spectral gap. If we look at the function which is the determinant of I minus ZA, that looks a lot like the characteristic polynomial. It's more or less the characteristic, it is the characteristic polynomial written backwards up to multiplication by a power of the variable. And so it factors, the non-zero part of it factors like this. So it factors like this. It's the product of 1 minus lambda IZ over the non-zero roots. I could also put in the 0 roots, but that would be just multiplying by 1, so I won't bother. Now, so if I consider the poles of the function, which is the reciprocal of 1 over the determinant of I minus ZA, well, those poles are the reciprocals of these non-zero numbers, lambda I. And this zeta A, by the way, is not out of a hat. This is the R10 Mazur zeta function for certain systems and shows up a lot. So one way of expressing the spectral gap provided by the Perron theorem is to say that if we look at the ratio 1 minus lambda z over the determinant of I minus ZA, this has a radius of convergence strictly greater than the radius of convergence of the zeta function, zeta A. Because all I did was to cancel out 1 minus lambda z. Okay? And now the other lambdas are smaller, so the other reciprocals are bigger, and so the radius of convergence went up. Okay, you'll see more of this probably in Pollicott's talks. Okay, and well, what about exponentially recurrent? An analogous fact is that if we take a look at the radius of convergence of 1 over the determinant of I minus f of z, this is 1 over lambda, and the radius of convergence of that multiplied by 1 minus lambda z is strictly larger. Okay, so this is a way of expressing the spectral gap, and actually it can be useful in some situations. And especially it becomes more meaningful in dynamical system situations in which this zeta function can be interpreted in terms of periodic points. Okay, now all three of these properties must fail if A is not exponentially recurrent. It's not that they might fail, they will fail. Okay, so this is kind of an important thing for the sharpness. It's the exponentially recurrent ones which are kind of the good old time religion, of the finite Perron theorem. Okay. Well, let's go back. So that's more or less the statements. So let's go back a little more and get to know these classes a little better. So we can make a table of possibilities for these four classes in terms of what the evaluations of f, t, and f prime can be at this radius of convergence 1 over lambda for t. All right. Now, if we look at the first column, Well, actually, before I look at this column, I want to call your attention to 3 facts which we want to have to justify this situation. So first of all, f evaluated at 1 over lambda is between 0. It's greater than 0 because we have a non-trivial system, and f has non-negative coefficients. But f of 1 over lambda is less than or equal to 1. Okay? It's impossible for f of 1 over lambda to equal 2. Okay, so that's something, some little exercise, in the definitions, but that's a key fact here. Okay, now so let's accept that. Now, if we accept that f of 1 over lambda is less than or equal to 1, then it's easy to see that f of 1 over lambda equals 1 if and only if t of 1 over lambda is equal to infinity. And that's because of this functional relation. Remember, we have this relation. Now, if f is between 0 and 1, well, the left side will be a finite positive number if f of z is less than 1, and then the right side will be finite. On the other hand, if f of z equals 1, and we think about what this means, well, clearly that will diverge, and the right side will diverge. Okay, so given the first fact, it's easy to see that the second fact holds. And now we understand what this first column is, because the definition of tangent is that t of 1 over lambda is finite. Okay, so that explains the first column. The second column is the definition. What about the last column? For null recurrent, for the derivative to be infinite for null recurrent, that's the definition. Infinite for positive recurrent, that's the definition. And it's a fact that, again, we can check that exponentially recurrent is in particular positive recurrent. Okay, so because ER is a subset of PR, this also holds. And in the tangent case, well, those tangent matrices, it could go either way. Okay, so I wrote down proofs of this in an appendix that we're unlikely to have any time for, but you can easily check when you get the access to the notes. Okay, so I'd like to try to give, again, a little more feel for what these classes are like. And for that, it's very helpful to think of loop graphs. Roughly speaking, loop graphs let you throw away the matrix and instead just think of a power series. To me, a power series is easier than a countable matrix. So here's some examples of loop graphs adapted for our purpose. So suppose we have f, not 0, and of course it's supposed to be the sum fn z to the n, with fn non-negative. We can define a loop graph as a label graph, which is the union of first return laps from a base vertex 1. Okay, so we have a base vertex. We have some other vertices. I have on this particular day, I'm considering loop graphs such that I have a first return loop. I have at most one first return loop to the base vertex of length n for every n. I don't need multiple return loops in this case. And what do I want? Well, I want these loops to have intersections only at 1. Okay, so any other vertex has a unique outgoing edge and a unique incoming edge. And I want the weight of the end loop when fn is not 0. When fn is not 0, then in this case, for example, I have f4 not 0. I label an edge to be definite such that the weight of that loop is f4. Okay? I could label edges in other ways to get a weight of F4. This is just for definiteness. Okay? So we can draw a graph. Now once we have a graph, of course, well, this is a graph, and if I assign integer indices to the vertices, keeping this assignment of 1 to the base, then I get some matrix A, which has this as its labeled graph. Okay, so from the series, I can draw the graph. I can think about the matrix A, which corresponds to this labeled graph. Okay, so it's a way of just translating from a series to the matrix very directly. All right, so here's an example. F of z is 3z plus z squared. What's A? It's a finite example. So A has first entry 3. And, well, the weight for z squared was 1, so I just have 1 and 1 here. And that's all there is. Okay. Now, for examples of these classes, it's often more transparent to consider the case lambda equals 1. If lambda is not equal to 1, you could take a look at the function f of z over lambda. Okay, and now, if f corresponds to Perron value lambda, then this capital F will correspond to Perron value 1. Okay, it's very easy to go back and forth between these. Really, the statements are kind of about z on the scale of 1 over lambda, and so this is a very natural change of variables to make things more straightforward. Okay, so let's suppose lambda is 1. Okay, so here's an example. We take f, which is some positive constant divided by, such that n squared is a positive constant, f sub n is a positive constant divided by n squared. Now, I think we see what the growth rate is for c over n squared. It's 1. And whether f of 1 equals 1 depends on the value that we choose for c. So if we choose c such that the sum here, when z is set equal to 1, is smaller than 1, then A is transient. Okay, we draw the loop graph, we have the matrix, it's transient. Okay, so there's sort of now if f of 1 is 1, then A will be recurrent by definition, and it will be null recurrent. Why? Well, take the derivative. N over n squared is 1 over n. So f prime at 1 over lambda is f prime at 1. It's just a multiple of the harmonic series, and it diverges. Okay, so once we get into the recurrent class and we look at this series, well, you see it has something to do with something that's kind of straightforward. Let's just take that n squared and make it an n cubed. Again, suppose f of 1 is 1. We're recurrent. The growth rate of fn is the same. It's 1. Now, if I take the derivative here, it's c over n squared. That converges. This A is positive recurrent. Okay? And, well, it's positive recurrent, but these the growth rate of these coefficients is still 1, right? So there's not a gap between the growth rate of the fn and lambda, and so this matrix is not exponentially recurrent. So these polynomial factors can mess up exponential recurrence. Let's take I always like simple examples. How about A, the 1 by 1 matrix 1? If we do the computations here, we see it is exponentially recurrent. Again, this is a finite matrix. Just as before, in this particular case, the growth rate of the fn's is 0. All right. Now, so now I'd like to say something about the something like robustness of the classes. Well, the whole situation is not very robust in some sense, right? You take an infinite matrix. Suppose you move every entry up by epsilon. Okay, now you square that matrix and every entry is infinite. Okay, so uniform perturbations are too coarse for consideration here. So to even say something like robustness, we can't think that coarsely. So I'll make a few statements and then I'll make some qualitative topological statement. So if A is exponentially recurrent, then there's some epsilon greater than 0 such that any matrix B which has the same 0 entries and satisfies 1 minus A epsilon times A smaller than B smaller than 1 plus epsilon times A must also be exponentially recurrent. So, well, why is this? Well, I didn't change the 0 entries. Okay, so what's happening here? Let's say at the 1 plus epsilon end, suppose I multiply by 1 plus epsilon. Well, I've just, what happens to those first return loops? The weight of an n loop gets multiplied by 1 plus epsilon to the n. Okay, so the spectral radius of the matrix 1 plus epsilon A, spectral radius of this function f for 1 plus epsilon to the A is going to be equal to the spectral radius of the function f for A divided by 1 over 1 plus epsilon. Okay, it doesn't change very much. Changes continuously as a function of epsilon. Same in the other direction. Okay, so it's kind of easy from the loops here to see that we have f changing continuously, and then t is also changing continuously. So if we have a gap between the radius of convergence of f and t, and we do this little perturbation, we'll still have a gap. And that's exponential recurrence. And because I didn't change the sign pattern, we also still have an aperiodic irreducible matrix. So this one is pretty easy to see. Here's another one that's pretty easy. Suppose A and B are recurrent and B is less than or equal to A, and B is not equal to A. Well, then the Perron value for B has to be smaller, right? Because otherwise, if they were the same, well, FA at 1 over lambda A would be bigger than FB of 1 over lambda A, which would be FB at 1 over lambda B, which would be 1, but it's impossible for, F at 1 over lambda to be bigger than 1. Okay, so if you go up from recurrent, to recurrent, the spectral radius has to change. If A is not exponentially recurrent, then there are many B such that lambda B is lambda A, B is not equal to A, and B is less than or equal to A. So here's something kind of concrete. Suppose that I take A. Let's just be simple for a moment. Suppose I take A and I multiply row 1 of A by some positive number smaller than 1. Okay. Then if I look at the function f, I associate to that new matrix, the radius of convergence is going to be the same. Okay. And then the entropy is going to have to be the same as well. And this matrix is going to have to be transient. I'm going to, okay, this is another topic. So I was riding in on the tram this morning. I thought there's maybe a nice way to say something qualitative. So we can consider the box topology on natural numbers by natural numbers, non-negative matrices. So what's the box topology? In the product topology, an open set is, if we were looking at the product topology here, we'd fix finitely many entries and allow them to vary by some epsilon. Okay. So, what's a basic neighborhood of A is a set of B such that for all entries ij, the absolute value of bij minus aij is less than epsilon ij. Okay, so now I'm requiring the entries to be close in every, the matrices to be close in every entry, and close can change the meaning of close can change with the entry. Okay, so this is not a coarse topology, it's too fine, generally speaking, but the statement we can make here is that if we, and this is an exercise, I think, in the box topology, the set of exponentially recurrent matrices is an open set, and the transient matrices are an open set. Okay, so it gives you some little feel. The others are not open. Okay. All right, now to stochasticization. Well, I did this earlier, but it's a trick well worth repeating, especially if, like me, you're a one-trick pony. So suppose A is a non-negative matrix, finite or countable, and R is a strictly positive right eigenvector. So A is beta times R for some positive beta. Then we can define a diagonal matrix R such that the ith entry along the diagonal is just the ith entry of that positive eigenvector. Then we can write P as R inverse times 1 over beta times A times R. And if you do the computation, you see, lo and behold, the column vector V with every entry 1 is a vector such that P times V is V. Okay? So that's saying that, well, what is P times V? It's the vector of row sums. Every row sum is 1. The matrix is non-negative. The matrix is stochastic. So this is stochasticizing the matrix A. Now, if A has only one positive eigenvector up to scalar multiples, for example, if A is recurrent, then there's only one stochasticization. Okay, so you have a canonical stochasticization of the matrix. So you can really think of it as being probability. Especially if you think of the steps, well, if you take your matrix and you multiply by 1 over lambda, you're not changing it whether it's transient, exponentially recurrent, etc. All you're doing is just rescaling lambda. Okay, so the qualitative properties don't change. If you take the positive diagonal similarity, what happens to these functions defined by loops? They don't change at all. When you go around a loop, you get a cancellation. Okay, so the f and the t don't change at all under the positive diagonal similarity. Okay, so these things you should think of as being, very close. Okay, so you can kind of then think, well, at least especially in the recurrent case, you can really think of the recurrent matrix as being very tightly associated to its stochasticization. Okay, now for this stochasticization, T of 1 can be thought of as the expected number of returns to a base state. You can think of the stochasticization as defining a Markov chain, right? And you take what's the weight of a loop? It's a probability of a certain way of returning to 1 conditioned on starting in 1. You add up all the weights of all the return loops, you're getting the expected number of returns in all future time. Okay, so so the recurrence then is saying that you expect to come back infinitely often. Okay, now if you take, now for tangent, you know, this is more heuristic. If we take a tangent matrix and we multiply it by 1 over its Perron value, so we have that we have a matrix with Perron value 1. Well, if we think of the entries of that matrix as being like the entries of a stochastic matrix, well, then transience means you know, that the expected number of returns is finite. And if we have a matrix which is transient in the sense of the probability theory of Markov chains, and if its Perron value is 1, so stochastic and its Perron value is 1, then it will be transient in the probabilistic sense of having a finite number of expected returns to the base state, if and only if it's transient in the sense of the Perron value. Okay, so everything's fine except in the transient case, as we've already seen, you know, you can have a stochastic matrix which has a Perron value which is smaller than 1. Okay, and then probabilistically, you could see an expected infinite number of returns to the origin, but it would be transient in the sense of this notation terminology for the Perron value. So that's a point where there's a kind of conflict of terminology for transient. So the terminology is kind of good in that you connect to the intuition of probability, but you have to remember that there's some caveats in the transient case. Okay, so I'm following Kitchens in using these terms, transient, null recurrent, and positive recurrent. Vere-Jones was using R transitive for transient, R null recurrent for null recurrent, R positive recurrent for positive recurrent, where R is the radius of convergence of T. So his capital R is R 1 over lambda. Okay, so he's talking about these things at the radius of convergence. So why do I follow Kitchens? Well, he's a pal. But you know, there's some kind of intuition in what he's writing, and it's a little less technical speaking. And you know, the evolution of English, especially American English, is to kind of dissolve into no structure. So I'm being a barbarian in that way. As far as the exponentially recurrent goes, this is something I just wrote down for this lecture because I think it's easy to remember, and it's all about exponential convergence and exponential spectral gap. It's all about exponentialness. Okay. Now, for matrices, at least in '62, Vere-Jones had a paper on geometric ergodicity of Markov chains, and so for him, an exponentially recurrent stochastic matrix was geometrically ergodic. You know, geometrically, exponentially convergent in some sense. Gurevich and Savchenko have an opus, including this. They called them, I think, stable positive recurrent matrices. They had some good reasons, but what does stable mean? I don't think it's as self-evident as exponentially recurrent. Okay. As far as references goes, when I go to Google and do a little searching, you know, by far the most popular reference is a book that's been around a long time by Eugene Sonetta, and is pretty old now. And then the next one is Kitchens. So it's like Kitchens loses 500 to 2,000. But they're both you know, looked at quite a bit. And so I certainly took a good look at Kitchens' book when I was preparing this this lecture. Okay. All right. So how do we define these Perron eigenvectors that are obtained in the Vere-Jones theory? Where do they come from? Okay. Well, so given our accountable irreducible and aperiodic matrix A and our choice of vertex 1, for each state j, each positive integer n, we define a number L1j of n. Okay, so this is the weight of the n paths from 1 to j that don't hit 1 in between. Okay, we're at the base. Somehow, you know, in the background there are these loops at the base, but other things are happening in the matrix. So at some point you have to not only look at first return loops to the base, but how you can go from the base to something else. And the repetitions are kind of built into the first returns, right? So when you look at how you go from the base to something else, you're going to be involving a path that goes from the base vertex to j, which doesn't hit this base vertex in between. Okay. Any path from the base vertex to j will be some number of first return loops followed by a path which does not hit the base vertex. Okay, so this guy, L1j, is this L1, little L1j is that number, and then you make this a formal power series, capital L1j, by making this little L1j of n the coefficient of, well, this is z to the n. The n is written a little small. Okay, z to the n. That's kind of what it has to be. Okay, so and then similarly, you can define R1 of n, R1n. Here's one, lots of ways to come back, and then so here we have, let's see, L1 used I. And then likewise, we can look at paths from j to n which don't hit 1 on the way to j. And that gives rise to you know, the same notion. We have numbers little r1j of n, adding up those weights for the paths of length n from j to 1, which don't hit 1 until the end. And then again, we get our formal power series. So there's the L, and then there's the R. Okay. Okay, so now we can not prove but state what these vectors little l and r are for our recurrent matrix, which are going to be the eigenvectors for the Perron value. Okay, well, we just take the row vector, whose jth entry is big L1j evaluated at 1 over lambda. Okay, and likewise for R, we evaluate Ri1 at 1 over lambda. Okay, so it's kind of a, you can see this is getting a little bit complicated, but you have some nice well-defined power series. And now, what's L11? L11, well, now we'd be looking at paths from 1 to I where I is 1, and we don't hit I in between. So L11 of z is just our function f of z. R11 of z is just our function f of z. Okay? So we evaluate those at 1 over lambda, we're going to get 1 if we're in the recurrent case, which we are. Okay, so that's fine. Now what about, so that looks pretty good. Now what about these other series, L1j and RJ1? Well, let's consider this equality here is supposed to be a product. Suppose we take the product L1j times RJ1. Okay, they're not the same. We're taking the product. Then we're looking at if we take this product. What we're looking at are paths which are concatenations of the following kinds of paths. Paths from 1 to j, now this is a j, which don't hit 1, times paths, concatenated with paths from j to 1, which don't hit 1. Okay? So these are first return loops. So the weights of coefficients for that product correspond to weights of first return loops which hit j. Okay? Not all first return loops, probably, but the ones that hit j. Okay? Well, that means that it's going to be, if I take that product, the coefficient of z to the n is going to be less than or equal to fn. Okay? So when I evaluate it 1 over lambda, okay, the product's going to be less than or equal to 1. In particular, those will converge. Okay? All right. Now, how bad can they be? Well, if you take any stochastic matrix, think again of this diagonal similarity with a matrix which is positive diagonal. You could put a huge entry on one side and compensate with a very small one. It's reciprocal on the other. What happens to the matrix A? The matrix A could develop some really huge entries and some very small entries. Okay, so without changing these series F and T at all. Okay, so just this kind of superficial similarity could drastically change the superficial appearance of the matrix. So when you come to these loops, you've avoided all of that because everything is canceling. Now those superficial hugenesses can be reflected in these vectors little l and little r. But if you stochasticize so that on your column vector is 1, what happens to your row vector is that it becomes a product L of I times R of I in the ith entry. Okay, so that is now standard and much more reflective of what's going on with the matrix. Okay, anyway, so the proof, as you see, it starts to get intricate, and you want to have some you need more. There are more series that are coming in. There are more recursion relations. There are also estimates. Kind of complicated. Okay, now here are the proofs in the appendix that I'm not going to do, but you can kind of see by how quickly I'm moving through, they're not too hard. I want to say one more thing before finishing. This is a finite approximation for eigenvectors. So if we have our n by n natural numbers by natural numbers recurrent matrix, let's consider an increasing sequence of subsets of the natural numbers whose union is the natural numbers, and such that for each of these sets Sk, the principal submatrix of A on that index set is primitive. Okay? This is a way of looking at primitive matrices from within having a limit which is A. Okay, so now let's let AK be the infinite matrix, which is Aij if I and j are in the index set and 0 otherwise. So you can just kind of think of a finite corner, perhaps, of the matrix, which is primitive. The other entries are 0. Now let's let Rk be a non-negative right eigenvector of A sub k necessarily for the Perron value of A sub k. And we can look at these eigenvectors and normalize them so that for some element of our first index set, 1 perhaps, we set R sub k at that index to be 1 for all k. So we kind of normalized our choice. Okay. Now, we already know by claim that the limit of the Perron values of these AKs increases to lambda. However, in the recurrent case, the RKs converge to a vector R, which is a right eigenvector for the Perron value. Okay? So this is something good, something you want. Okay? Now, if you're in that's the recurrent case. If you're in the transient case, I'll say this instead of writing because of the time. If you're in the transient case and you do this, what happens? What happens is that you get take the lim inf of define, you have a sequence Rk, define its lim inf coordinate wise. Okay, so the lim inf converges. You have some sequence and a lim-inf of these rk's. That gives you some vector r. But now, in the transient case, it's not that ar is lambda r. Ar is less than or equal to lambda r, and ar is not equal to lambda r. Okay? So if you were just approaching these infinite matrices in the most natural way and just trying to do finite approximations, your proof wouldn't quite work. It would go wrong. Okay? And I'm sure that somewhere there's a more sophisticated appreciation of exactly how it goes wrong in the transient case, but since I don't know how to say that and I'm out of time, I won't. Thank you.